Hey students, we're going to be looking at the limits of things called difference quotients. Difference quotient, subtraction division. I know one thing that's a subtraction division. That's like this guy. You thought I was going to write it upside down, didn't you? Which we call a slope. That guy is a difference quotient because we've got differences and we're quotienting them. See what I did there? Okay. So here we're really beginning to look at limits of slopes. We're going to see what that means in a minute. And again, you're going to see some Khan Academy assignments here to check your understanding on your own version of this. Here is a graph that we're going to look at in Desmos, and I'm going to ask you to play around to try to make some sense of these two questions. Please pause, try it out, and come back and let's see if we can answer them. All right, so my two identified points are something like x, y, and I'm going to call that f of x instead of y. And then my other point is going to be x plus h and f of x plus h. Cool. Let's see if I put parentheses in the right places. I need another one there. Nope, I don't need another one there. Erase, erase, erase. That's a plus, not a parentheses. And I need parentheses to close out the coordinates. Beautiful. Average rate of change between these two identified points. Well, that's a slope. So that would be something like f of x plus h minus f of x. Who knows what those actually are? And then x plus h minus x. I really like writing this way. We could just kind of get rid of those x's and keep an h, but I can see that this is a slope. We've got a y2 minus y1, x2 minus x1. We can kind of work with that. Okay, so what happens is we slide the green points closer to the blue points. Well, there are a couple things that are happening here. The first is that the x distances are getting closer and closer together. Those are caused by that h distance between them. So the first thing that's happening here is that the h is getting closer and closer to 0. The second thing that's going to happen here is that instead of looking at 2 points, we're going to begin trying to find the slope of 1 point. And that might be a little bit problematic because you might notice that that disappears the second they get to each other. And the other piece of that is that we kind of predict we'd have an issue there. Because if h becomes 0, we end up with 0 over 0 for this slope. And that's weird. All right, same thing we're going to look at. Same equation. I'm going to look at some values to get closer and closer to these 2 points being the same, which magically have now appeared on your document. What we did was find the slope between these 2 points using the y values calculated from the equation and the x values given there. The other thing that I notated here were the h values, how far apart these 2 points are. So if we're using x for 1, and then we've got x plus h is our second value, which is 3. That's one way to kind of contemplate that. I also don't know why this slid in a weird way, but that's okay. So what we're really doing is finding the slopes. And as we move closer and closer and closer together for these points, the h value is really decreasing here. One way for us to describe this is to say that this is the limit as h approaches 0 of our y coordinate, f of x plus h for our second one, minus f of x, and then that's going to be divided by x plus h minus x. And this should look really familiar because we saw this on the previous page. This is all about finding slopes that get closer and closer to being 1 point. In other words, if you could actually get to 0, you would find the slope at a specific point, which we call the instantaneous rate of change. I'm going to write that as ROC for rate of change because I don't really have the room for that. And I'm going to add one more piece to this, that that this thing, which allows us to find the slope at a single point, we're going to give a special name to. This is going to be called the definition of derivative, and this is going to be a derivative. So if you ever see something being referred to as the definition of derivative, this is what we're really talking about. So I'm going to call this the definition of derivative. And the next chunk of stuff that we do in calculus is going to be based on learning all about how to use derivatives, find shortcuts for derivatives, so we don't have to do this all the time. This is kind of a pain in the neck. And then from there, we're going to be learning about how we can use derivatives to understand things. Looking at this specific definition, we're going to have another way to look at this in a second, but we're going to play with this to see how it works with an easier function. So picking a linear function, I don't know, I'm going to call this g of x is equal to 2x minus 7. We know that's going to be a line that has slope of 2 and a y-intercept of negative 7. So what if I then apply this definition of derivative? So we take the limit as h approaches 0 of, here it's going to be g of x plus h. So whenever I see an x, I'm going to put in x plus h. And that's going to be 2x plus h minus 7. Cool. Minus g of x, so minus 2x minus 7. I like it. And then the bottom we've got x plus h minus h. Sorry, minus x rather. Let's do some simplifying. When we simplify some things, you might pretty quickly see that the bottom is going to become just an h, which is a little bit problematic based on, we're plugging 0 in a minute. On the top, we've got 2x plus 2h minus 7. And then for my other part, it's going to be minus 2x plus 7 once we distribute that negative. You might be completely unsurprised that the biggest mistake that my students tend to make is losing negatives in this part, or plugging x plus h in incorrectly. Remember, this is a composition of functions. That's why we spent some time in that over the summer or at the beginning of the school year, and that we have to plug that whole thing into whatever function we have. All right, I've got some more stuff I can reduce. 2x minus 2x, negative 7 plus 7, and I'm left with the limit as h approaches 0 of 2h over h, which you might recognize that we can cancel those h's out, leaving you with just 2. What I'd like for us to pay attention to is this number 2. This slope that is instantaneous at, I guess, any point along this line is the same slope that we predicted with our equation. What the derivative is an equation for the slope at any point along any equation that we can take the derivative of. This is a really important thing for us to do. This lets us find rates of change for things that are changing in really crazy ways, not just lines. So we're going to be able to look at slope of any function we can figure out. I want to spend a second talking about another way to think about the definition of derivative, and I'm just going to add a blank page for that. So this is it's often called the alternative definition of a derivative at a point. And we're going to see this come up a bunch too. It's using the same idea. So if I have some kind of smooth curve, and I've got 2 points on this curve, this time I'm going to define this as some kind of a known point. Let's talk about this as the point a comma b, or a comma f of a. And then we have an unknown point. That's going to be x comma f of x. If we do the same thing, if we make this point approach that other point, in other words, we're saying that x is going to get close to a. Thinking about that in terms of derivative, that's a limit. So this is the limit as x approaches a. And we're going to do a slope again. This is going to be f of x minus f of a. We probably know what that number is. And then on the bottom, it's going to be x minus a. One of the things that you might notice here is that, once again, we're going to end up with 0 over 0 if we plug that in. Which, again, that's something that we're expecting. But this will let us find the value of a derivative at a point without having to plug something in. There are times that one or the other is more useful. All right, let's try one kind of fancy function. Here we've got x squared minus 4x. And what we're trying to do is to, first, we're going to have to find the derivative of this because we're going to need the slope of this in a couple minutes. I'd like to take a look at the instructions down below because that's going to be kind of guiding why we're doing this. So we're looking for an equation of a line tangent to this point. What that means is that we'd have some kind of a point that we have a line that's just touching, and my diagram is terrible because I am not a great artist, but that's okay. And if we can figure out what the slope of this line should be and what point that is, and here we've got the point 2 comma negative 4, that'll give us an equation for that. We also have this thing called a normal, and a normal is going to be the same thing but perpendicular to that tangent line. Both of these are useful things in lots of applications. All right, let's start with this function up here. So for slope at a point, we need to take the derivative because that will tell us the instantaneous rate of change, aka the slope. So if we say that this is the limit as h approaches 0, I'm going to write this out in formal notation. F of x plus h minus f of x over x plus h minus x. I'm going to plug in this function. So this is going to be the limit as h approaches 0. And in my difference quotient, f of x plus h is going to be x plus h squared minus 4x plus h. I'm going to switch colors just to keep things a little bit easier to see. Minus that original function, x squared minus 4x. All right, and then on the bottom, x plus h minus x. I'm going to acknowledge that that's just going to become h before I jump to the next line. Cool, let's multiply some stuff out, do some distribution. And when we do that, I'm going to have the limit as h approaches 0. X plus h quantity squared is going to be x squared plus 2xh plus h squared minus 4x plus h. That's going to be minus 4x minus 4h. Let me extend my vinculum or fraction bar. Then we get minus x squared, and then minus negative 4x, so plus 4x. And here's where the magic kind of happens. This is a really cool thing because you can check to see if you've done things in a way that works, or if you've done the math correctly, because we should be seeing things cancel out. X squareds are canceling out. I've got minus 4x plus 4x, those cancel out. And suddenly the only things that I have left are parts of the numerator that have an h. So we've got the limit as h approaches 0 of this beautiful fraction, 2xh plus h squared minus 4h. And you might notice that since all of those pieces have an h, I could factor something out and reduce that. And at that point, I'm going to have the limit as h approaches 0. Factoring out an h and canceling with the bottom is going to leave me with 2x plus h minus 4. And finally, when I plug in my 0 for h, I'm left with 2x minus 4. We say that this is the derivative of g of x. We've got a couple different ways to notate this, one of which is to use the notation that we are going to call g prime, where we have basically an apostrophe within this function notation to show this is the derivative of that function g. Cool. And again, I want us to remember that this g prime, this derivative, this is slope. This is a really important thing for us to keep in our heads at all times, that this is the slope of this parabola. So this parabola looks something like this. And the equation 2x minus 4 tells us what the slope of this parabola is at any point along it, what that instantaneous rate of change is. So at the point 2 comma negative 4, which is going to be somewhere, I think that's actually going to end up being the vertex. I may be wrong, but that seems like that's it for me. I don't know, I'm going to see in a second. We can plug in that point into our derivative. What that's going to tell us is the numerical value for the slope at this point. So g prime of 2 is going to be 2 times 2 is 4, minus 4 is 0. This is horizontal. The equation for the tangent line is going to be a y equals negative 4 equation because we have a horizontal slope. You could also have written that as negative 4 plus 0x, and that would have been okay. For a normal line, so now we're talking about a vertical line, we're going to end up with x equals 2 for this normal.